Hey there, welcome back to CMTEQ channel. In this tutorial, we're going to look at how you can create an analog to digital converter, basically using the Arduino, some basic electronic circuitry. As you can see here, the yellow signal is a PWM signal and the red signal here is the analog signal on the output of the op-amp. So let's get started. Now, to design a digital to analog converter, we need a digital signal and the analog converter part. So Arduino will basically be the device that will create a digital signal for us. So we're going to have an Arduino with a PWM code. Then the next stage on our setup will be a low pass filter to basically create a small circuitry that's going to block the Arduino PWM signal, but only pass the voltage level. We don't want the frequency component of the PWM signal. We only want the voltage component. So we're going to create a low pass filter. The next stage will then be to take a non-inverting operational amplifier that will then be fed from the low pass filter signal and set up the non-inverting op-amp with a gain that will basically amplify the input from the low pass filter to give us the analog signal level that we want, and that's going to be proportional to what the PWM signal will be doing here. So whatever the level of the PWM signal will be, that will be translated to a low pass signal here, and that will then be fed to the op-amp with the gain that we're going to set up. The op-amp will then give us the appropriate analog signal level. Great, so let's start designing our DAC circuit. So first thing, we need to pull in the Arduino into our environment here. Great, then we need power for the Arduino. So we're gonna power this Arduino with a 5-volt supply, and we need a ground as well. Okay, so I'm gonna connect the ground signal and the VCC signal. Let's give this VCC signal a VCC. Great. Then the next thing is we need the output for the Arduino that is going to be our PWM pin. So I'm going to select, as per our tutorial here, we're gonna select pin 9. Then I'm going to rename this as PWM. Okay. Next, we need to connect the oscilloscope so that we can view our PWM signal. To do that, right click, place virtual instrument oscilloscope, and we're going to place it right here. Then we're gonna connect the PWM output here to channel A, which is the yellow signal. Great. Now, if we run this, we're gonna get an error because there is no code yet. Okay, so if you click on property, edit property, you're going to realize that there is absolutely no code here, so we need a code. So I open up my Arduino interface. I'm going to paste the code here. Right now, this code is very much self-explanatory. This is a simple code that will create a PWM signal that's basically going to vary the duty cycle from 0 to 100% and start decreasing from 100% to 0%. Now, let me take you quickly through this code. So the first line is we basically defining the pin 9 as the PWM pin. We're setting it as an output, right? Then we're creating a for loop here with the variable value that's now going to be increased from 0 to 255, as you can see here. Now, the loop is going to fail when value become equal or greater than 255. Then the loop will exit. And we're taking the value and we're passing it to the analog write function with the PWM pin and the value. Then these will basically create a PWM signal for us. Then we basically repeating the same thing here, but in reverse mode to basically decrease from 100% to 0% duty cycle. Now, if you want to know more about how to generate PWM signal with Arduino, this is just one way. I have a tutorial where I went through the process of creating PWM signal with 4 different methods. This is method 1. So there are 4 more methods that you can do. With this method, your PWM signal frequency is very much limited. So if you want higher frequency, you have to watch the other methods on my tutorial. Great. And that tutorial is on the description box of this tutorial. Now let's go ahead and build this code. Make sure you've got your target board selected and COM port if you've got your physical device connected. So I'm going to build this quickly. Compile. Great. Compilation down, no problem. But now, since we want to basically import the hex file and load it onto our Arduino here on the Proteus simulation, so what we have to do here is very simple. We need to go on Sketch and we must export the compiled binary. So it's going to compile it again, but this time it's going to export the hex file for us. Great. And the hex file is going to be found on the folder where this Arduino file is located. Great. So what I'm going to do now here, I'm going to come onto my Arduino, edit property. Then I need to load the hex file, program file. I'm going to click on the folder icon. Then I already have a link where the hex file was generated. I'm going to paste it here and I'm going to say open. Then I'm going to get to this point here. Then I need to select either the hex file or the .elf. So I'm going to take the hex file. I'm going to say open and OK. Now let's go ahead and run this so that we can ensure that we're getting our PWM signal before we can move to the low pass filter block diagram. Because remember, this is the first block diagram where we generate a PWM signal, then the low pass filter, then the non-inverting op-amp block diagram. So I'm going to go ahead and click on run here. Our oscilloscope pop up and we can see the PWM signal on the yellow channel here. Okay, now I'm going to set up the correct setting for channel A and channel C, because channel A got our PWM and channel C we're going to put the analog signal there. The other channel here we can turn them off. Let's turn this channel off. Okay, then let me just increase the divisions here on this channel here. Okay, and set it to the coupling, DC coupling, this channel as well. And then I need to just center it a bit. Great. Then we need to do the same on channel C. Now you can see that channel C, there's nothing connected and it's sitting right at 0. Now when we set up the analog part, the conversion, then you're going to see the signal on channel C is going to be moving up and down as the PWM signal to T cycle changes. Now I'm going to stop this and then move to the low pass filter. Now, by the way, if you find this tutorial useful, please make sure you give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. So for our low pass filter, all we need is the resistor. Okay, so I'm going to place my resistor and we need a capacitor here. So let's bring our electrolytic capacitor here. Now you can calculate how much frequency will be your cutoff frequency, basically by calculating 1 over 2 pi RC. That will basically be your formula to calculate the FC, the cutoff frequency. So with this value here of 10K, and I'm going to change this to a 10 microfarad. Right, so this value will basically give me a cutoff frequency of basically 1 Hertz. So we basically gonna make sure we don't have any frequency component, but you can decide which value you want to use for your particular design requirement. So I'm going to just paste this. Great. Now what I've done here, basically I've included a voltmeter across my RC output, right? And the output is connected to channel C and the input is obviously from the PWM. So I'm going to go ahead and give this a run now. So what's going to happen here, we're going to basically get the output of the RC is only going to go up to the PWM level, as we know that PWM is only going up to 5 volt, which is the voltage range of the Arduino output here. So if we want this to go to 10 volt, that will be the next level where we're going to use the op-amp to basically do a level shifting here. Right now, this is only going to go up to 0.5 volt. As you can see, channel C here is increasing slowly here as the PWM is changing. Now, This is not running in real time now because of the CPU being overloaded. That's what always happens with the Proteus simulation. So basically, as the PWM duty cycle increases to reach 100%, the voltage is also increasing. And right now we're sitting at 3.5, 3.6, and the PWM is also increasing its duty cycle. Now, when the PWM signal get to 100%, this voltage is going to be kept at just below 5 volt. Okay, so if you're looking to get a 0 to 10 volt, you need the extra stage. So that will be the next stage that we're going to now implement, so we can get a 0 to 10 volt. This tutorial is basically part 2. Part 1 of this tutorial is where I implemented this using the physical hardware, basically the RC filter and the Arduino, to basically create this digital to analog converter. So as you can see, the value is almost 5 volt and the PWM duty cycle is nearly 100% today. So if you want to know how this DAC operates in real time, please watch part 1 of this tutorial where I implemented this with the physical devices. Now let's move on now to the next block diagram here, the op-amp, the non-inverting, to basically create that 0 to 10 volt signal that we are looking for. Now to get the 0 to 10 volt going, I'm going to use the amplifier, basically the LM741. You can also use the 324 or the LM211. It doesn't matter so long as you can configure your op-amp as a non-inverting amplifier with the gain set to basically amplify the signal here. You can see this signal is going from 0 to 5 volt. Now if you give this op-amp a gain of 2, that will basically take whatever signal that is on input, it will multiply it by 2. Okay, so let's connect the non-inverting onto the output of our RC filter. Then we need 2 resistors to basically set up the gain. Okay, so the one resistor, this will be our RF, the feedback resistor, that will be connected as a negative feedback. Okay, and we need a second resistor that will set up a voltage divider with the feedback resistor here, and the output of this voltage divider, we then connect it to the inverting input. Then we need a ground connection for R3 here. Now the gain of the non-inverting amplifier is basically RF divided by R3. So R2 divided by R3 plus 1. So if these two values are 10, they will basically give you 1 plus 1, it's 2. So this circuit here gives us a gain of 2. That gain of 2 means we will multiply it with the whatever that will be on the input. So the highest here will be, let's say 4.8 or 4.9. We multiply it by 2, we're going to get almost 10 volt. Now, it is important to note that your op-amp will only give you a voltage based on what is connected across its plus V and minus V terminal. So let's put the minus V connected to ground here, and the plus V, we're going to basically connect the voltage that we want. So let's bring the power here, and we're going to connect a positive 12 volt on this terminal. So let me find, there is no positive 12 volt, so we need a plus 12 volt. So this basically means the op-amp will amplify a signal to go closer to its plus V terminal, but it will not going to get to 12 volt. It will get to something like 80%. Now you have to check the datasheet of your op-amp to see to how much its output can amplify to. Now regardless of your gain here, your op-amp cannot go beyond the 12 volt. If you, let's say you put a gain of 3, it basically means the highest will be 5 on the input times 3, that will give you 15. But no, you're not going to get 15. You will be limited to what your op-amp is able to give based on what is connected to it. Now the LM741 also got a voltage limit, a maximum voltage you can connect to it. So you cannot connect 100 volt to it and expect to put a gain of 2 here and hope getting a 200 volt on the output. So that's not going to work for you. So in short, your op-amp would only amplify up to its terminal, but it will not also get to its terminal voltage. It will be just below the terminal voltage. depending on the data sheet, the configuration of your op-amp, it might be 80% of its terminal, or 90%, or even 70%. So you have to check your op-amp data sheet. But right now, with a 12 volt supply with a gain of 2 here, we are expecting to get at least a value that will be closer to 10 volt. Now, if you are using the LM741 op-amp here, there is pin 1 and pin 5 are the offset null pins. Now, this offset null pin basically means when your op-amp is powered, let's say you got your 12 volt and your ground connected, and plus and minus input have nothing connected to it, and you power your circuit, you're going to have a voltage on the output already. It's going to have some voltage already there. Now, if you want that voltage to be zero, you want it to be zero when there is no input voltage. So you basically need to connect a potentiometer, right? That will be connected across pin 5 and pin 1. And then the output of the potentiometer must be connected to your negative pins here. That way you can adjust that voltage output to be 0 volt. Now, this is very important if you are amplifying very small signal. Right now, we are amplifying a signal that is up to 5 volts, so we're not too concerned about that. But if you are amplifying millivolt signal and you're working with real devices, you need to make use of these offset null pins. Pin 5 and pin 1, you need to offset them, connect them, adjust them so that your output will be 0 when there is no input voltage. Okay, so now enough said about the op-amp amplifier here. Let's now connect our output. So I'm going to basically make a copy of this here. So I've connected the output of my op-amp to now channel B here, the blue channel. Now, before we run this, what I'm going to do, I'm going to bring in a voltmeter. First, let's connect the resistor here on the output here, because we want to basically connect an LED, a load, right? So that we can see as our PWM is going to be changing the duty cycle, we're also going to have a variation on our load. Okay, let's go ahead and add some multimeters here. So I'm going to add a DC ammeter so that we can measure the current that is going to be flowing on this LED here. Okay, so the lower the voltage, right, the lower the current, and that will define the brightness of this LED. So let's change this to milliamps, because we're not going to get amps there, because our op-amp here will not gonna be able to drive higher current. Then let's go ahead and also add a voltmeter on the output of that op-amp so we can also measure the DC voltage. Great. Now we need to connect this to ground. Now I just need to change this resistor to a value that will allow some current to flow in there, because 10K is definitely going to cut it for us. So let's go ahead and put a 330R. So that will basically mean 330 ohm resistor. Now we are ready to basically run this configuration of our digital to analog converter. So here we're going to see the voltage, the 0 to 10 voltage. Here we're going to see the 0 to 5 voltage, and this is going to show us the current flowing through the output LED. So now let's go ahead and give this a quick run. And as you can see, the PWM signal is increasing, right? We are at a certain duty cycle here, and the voltage on the output here of our RC filter is 1.2, and the voltage on the output of the op-amp is 2.6 and increasing. You can see with a gain of 2, if we got 1.5 here, you basically gonna have 3 volt. So it basically multiplies. And as this voltage here increases, the current is also increasing here, and this LED is getting brighter and brighter because we got much higher voltage pushing the current. And on the oscilloscope here, you can see that the red channel, which is channel C, that got a 0 to 5 volt, is way behind the blue channel, which now is going to go all the way up to 10 volt. Okay, so that's it, the difference on the level shifting that we wanted. Okay, so we want to go from 0 to 10 volt. So we take the low signal of 0 to 5 volt and shift it to 0 to 10 volt, with a non-inverting op-amp and a gain of 2. Okay, as you can see now, our input voltage is 4.5 and the output here is 9.2 and the LED is brighter. We got 21 milliamps of current flowing. So this is basically how you can change the yellow PWM signal into a continuous analog signal. So thank you for watching. If you found this useful, please make sure you subscribe and stay tuned, because part 3 of this tutorial, I'm going to basically take this to the real and physical device with a real Arduino, an op-amp and an RC filter to basically get what we have on the simulation here running onto the real device. Until next time, cheers.